start by adding my thanks to the organizers of this wonderful conference and even more wonderful program. Adam, Christian, Matt, and Laura, who's no longer with us here. But she was very much here for the first week and a half, I think. So my talk is a departure from the center of gravity of this conference, but I'm glad that by now several others have spoken a little bit far from the center of gravity. No quantum information and no diagrams. I've been enjoying the diagrams over the last weeks very much. Well, one kind of diagram of implications, but in the more traditional mathematical sense. So the Levy-Khintchine formula is a central result in classical probability, and it gives a canonical representation of the characteristic function of probability distribution, which is infinitely divisible. And it expresses it in terms of a Gaussian part, mean and variance, and a jump part. So the object of this talk is to quantize that to some extent. And this has some history. My main, first of all, classically, the original result is for a probability distribution on the line, but then it was realized that it could be extended to a group, a Lie group, and that extension was done 70 years ago by Hunt, and that's known as Hunt's formula. So from a classical Lie group to some quantum Lie groups, or Q-deformed Lie groups. So that's the subject of my talk. It's, I'm reporting on joint work of Uwe Franz, Anna Kuhler, and Mikhail Skaider. And this is the rough plan. The first half will be explaining the problem and some of its aspects in general for compact quantum group G. And then the second half will be working specifically to solve the problem, so to speak, for SUQN. So we start with the Hopf algebra of a compact quantum group, which I shall use the letter A for. And the basic ingredient for problem and tackling the problem is a tower of star ideals of A, which starts with the kernel of the co-unit, and the nth one is the linear span of the n-fold product of elements from the kernel. So associated with this tower, we have, first of all, what I'm going to refer to as a standard projection P, which is projection onto the kernel along its natural complement, multiples of the identity element. And then further, a family of Q projections I'm going to refer to these. So these are projections onto the second ideal, K2, along some complementary subspace, J, which is closed under taking adjoints and contains the identity element. So this family are compatible with Q, and they are the fact that you're projecting along a star subspace translates to the projection being having this Hermitian property. So convolution semigroups of states. So there is the definition, and the appropriate continuity condition here is pointwise continuity in T. These are describable through their so-called generating functionals. So this is the natural analog of generator of a semigroup in semigroup theory. And the generators are characterized. They are Hermitian, vanish at the identity, and have a conditional positivity property. So gamma on C star C is non-negative for each C in K. So there's a one-to-one correspondence between these, differentiating a convolution semigroup. Differentiating a convolution semigroup at 0 gives you a generating functional, and exponentiating in the convolution sense at t times the generating functional gives you a convolution semigroup of states. And this works. The reason this is successful is we have no topology on A. However, apart from the topology of pointwise convergence, it works courtesy of the fundamental theorem of co-algebra. So we have to start off with this correspondence here, noticed by Schumann. So the simplest kinds of convolution, simplest kinds of generating functionals are drifts, and these are Hermitian epsilon derivations. And the drifts are precisely those that generate convolution semigroups of characters. So that sits inside the correspondence. Now, we need another kind of map, which will provide dilation of convolution semigroups. In fact, stochastic dilation. So the second kind of map is we call a structure map. So this is a map from the CQG algebra A into ANDed operators on a Hilbert space with one additional dimension, okay, C plus K, and satisfies this structure relation, which can be thought of as a departure from being a derivation, epsilon derivation, and the departure is encapsulated in the right-hand side. From a stochastic point of view, this turns out to be an Ito correction to being a derivation. Different ways to describe that. Well, in terms of its action on elements of the form C star C, where C is in K, this relation reduces to this, and combined with killing the identity element and being Hermitian, it's another way to characterize a structure map. And in terms of its block matrix decomposition, this is saying that the bottom right, the top left is a generating functional, as just described. The bottom right term is a representation composed with a standard projection, and the off-diagonal term is a rho epsilon derivation. So we can write the rho epsilon derivation condition in terms of action on K, because it kills the identity element, like this. So eta on C star C is the adjoint of rho C times eta C. And the top left is a generating functional which relates to the derivation through this formula here. So gamma on C star C is not just non-negative to be a generating functional, its value is the square norm of e to c. Okay. So I think I'm going to show these two slides in the reverse order. So from a structure map is a component of a structure map is a generating functional, and Schumann realized that there's a converse to this. Given a generating functional gamma, we can fill out a block matrix and form a structure map in this fashion. So any generating functional is the top left of a corner of a structure map. And this construction is unique up to a natural notion of unitary equivalence. So we talk about the structure map associated with a generating functional. We'll do that frequently. And in the trivial case, where gamma is a drift, there is no need to dilate. In other words, this is true with k trivial. Okay, so that's another correspondence: generating functionals, convolution semigroups of states, structure maps up to a notion of equivalence. Schumann also discovered that you can associate to a structure map a quantum counterpart to a Levy process. So this slide is the only slide with any detail on the stochastic picture behind everything that's being discussed here. So a quantum Levy process is independent, identically distributed increments process, or stationary in time, quantum process. And by quantum process is meant a suitably adapted family of maps from the algebra into bounded operators on a Fock space of this form. So the K here, which becomes the multiplicity space of the noise that drives the associated quantum Levy process, is K in this block matrix structure map. And so we can associate a quantum Levy process, and this again is unique up to a natural notion of equivalence. And in fact, we can describe the associated process in this fashion here. So it's governed by a quantum convolution counterpart to a stochastic differential equation. I'll make some small reference to that later. Okay. So structure maps can be summed in this simple fashion. If we have two structure maps on the same CQG algebra with multiplicity spaces K1 and K2, phi1 and phi2, then this procedure here defines a structure map with multiplicity space K1 plus K2. So we've taken the direct sum of the representations here, and in a sense the direct sum of the derivations and the corresponding generating functional part. Just summed these. So a simple class of structure maps, or the inner structure maps. So these are given a representation rho. The inner structure maps are defined by this formula here, in which eta rho zeta is the inner derivation determined by vector zeta, so it's determined by a vector zeta in the multiplicity space, and the generating functional is then the vector state determined by the vector zeta, composed with rho composed with the standard projection here. So inner structure maps take this form here. So that's a simple class, and we're going to be interested later on in approximating by inner structure maps. So a key problem in, it turns out, in the Levy-Khintchine, the issue of finding a Levy-Khintchine decomposition. So I'm going to be more precise about what is meant by that shortly, but it means in some sense dividing a generating functional into a Gaussian part and another part which is wholly non-Gaussian, has no Gaussian component. Okay, within the problem arises very naturally the question of completion. So completion is the idea that you fill out now the bottom row into a structure map. So given a representation and a derivation, rho and eta, can you find a gamma which completes to a structure map? Okay, so an example where you can is when you take an inner derivation, then that's completed, as we've just seen by this generating functional. Now, for the question of completion, a hint on a strategy for this is, suppose that we can solve this in this restricted sense. So we can find a functional gamma naught on the second ideal, in the dual of the second ideal, which is Hermitian, and satisfies this requirement here, that at C star C it's the square norm of eta C, then we can complete by letting gamma be the composition of this partial solution with any of our Q projections. Projection onto K2 along a star subspace containing the identity. Okay. So next stage is to approximate by inner derivations. And the key point here is the set of completable row derivations is pointwise closed. So that is proved by appealing to the idea on the previous slide. I shall say more about that, but it's as straightforward as this. And the upshot of that is that approximately inner derivations are completable. So getting towards our problem, so a generating functional, first of all, what does it mean for it to be Gaussian? Well, being Gaussian is loosening the condition for it to be a drift, which was to vanish on the second ideal, and it turns out that vanishing on the third ideal captures the Gaussian property in some sense. That's equivalent to the derivation of the structure map vanishing on the second ideal, or the representation vanishing on the first ideal, and that translates to rho being essentially the co-unit times an identity operator on some Hilbert space. So in particular, the structure map takes this form. It is 0 in the bottom right-hand corner. Now that gives an echo of Gaussianness itself, because if you solve a stochastic differential equation with a coefficient like that, then only terms involving eta and eta dagger are involved, and these are quantum counterparts of Brownian motions. Okay, so the question is, can we split any generating functional into a Gaussian part and a remainder part, where the remainder part is, in some sense, has no Gaussian part to it. So, given a representation, first thing we can do is we can identify this subspace of the representation space, which we'll call Kg, and that's the intersection of the kernel of all kernel of rho C, where C runs through the first ideal K. So that gives us this reduces the representation, and therefore also reduces the derivation. Okay, so and once you've done that, there's no Gaussian part in the to the remainder Hilbert space, Hilbert subspace. So what that does is it turns a structure map into a 3x3 block matrix, and we'll call any of the ingredients wholly non-Gaussian if the remainder part is all of K and it's non-zero. So the Gaussian part is trivial. So the question is, can e to g or e to r be completed to a generating functional? So that would give us, the upshot of that would give us gamma as a sum of a Gaussian part and a non-Gaussian part. So that's true because if you can do one of these completions, then you can do the other. So amongst the Q projections, if you're given a generating functional which is non-trivial, so it's not a drift, then you can find one of these Q projections which leaves the generating functional invariant. So here's a strategy for proving the Levy-Khintchine for a compact quantum group. So you take a generating functional which is not a drift. Then first of all, as we've seen, the Gaussian part of the representation composed with a standard projection is trivial. And if either e to g is completable to a structure map, it'll look like that, or e to r is completable to a structure map, then, as I've just mentioned, both complete. And so we have the following, that gamma at c star c, the structure relation is square norm of e to c, and that's the sum of the squares of e to gc and e to rc, which in turn are gamma 1 c star c and gamma 2 c star c. So the generating functionals gamma and the sum, gamma 1 plus gamma 2, agree on the second ideal, the linear span of c star c's c and k. So now we take one of these projections leaving gamma invariant, and then gamma 1 composed with q plus gamma 2 composed with q gives us a Levy-Khintchine decomposition. So this gives us a strategy for solving the problem, either showing that we can complete Gaussian structure maps, Gaussian derivations to a structure map, or wholly non-Gaussian derivations to a structure map. And the first way that this problem was solved for SUQ2 was to show that you can complete the Gaussian ones. So our first strategy in generalizing this to from 2 to n was to try and prove that. And quite quickly we found that that can't be done. So we switched strategy. In any case, we have the structure of this pattern of implications C stands for all derivations are completable. CG Gaussian ones are, and C, W, and G wholly non-Gaussian ones are. And each of these two implies the Levy-Khintchine property, which is decomposition into a Gaussian part and a wholly non-Gaussian part, as we've seen. So we're going to refine this tree of implications by introducing approximate innerness. So G has the approximate innerness property if every derivation with respect to a wholly non-Gaussian representation is approximately inner. So some remarks on that. We've seen approximately inner derivations are completable. So this property is a strengthening of the completability of wholly non-Gaussian derivations. Secondly, approximate innerness is a hereditary property. So if it holds for G, then it holds for all its subgroups. And in the classical case, wholly non-Gaussian generating functions are expressible in terms of a measure called the Levy measure through this formula here. So pi is the measure on the group, and these are approximately inner, and it's witnessed by approximating the corresponding derivation by these inner derivations here, cutting down to cutting down this expression to a complement of open neighborhood of the identity element. Okay. So here's the main theorem here. Main theorem is part 2. So part 1 I've already mentioned. The completability of Gaussian derivations is restricted to the case n less than or equal to 2. But for all n, the approximate innerness property holds, and therefore the Levy-Khintchine solves the Levy-Khintchine. Corollary of that, because the approximate innerness property is hereditary, is UQN also has a family have the approximate innerness property, therefore Levy-Khintchine, because UQN is realizable as a subgroup of SUQN plus 1. Okay, so there is a picture of the generators in relations for SUQN, and this, as a unital algebra, we have this way of describing Hopf algebra of SUQN, generated by n squared generators Uij and a element d, sensibly named d to the minus 1. Its role is to act as an inverse of the quantum determinant of the Uij's. So the star bialgebra structure, the extra structure, is determined by these formulae here. That's for UQN, and then for SUQN, we remove this extra generator and add the relation that the quantum determinant is 1. Okay, so some key takeaways from representation of from SUQN. I'm going to call SUQN AN from now on. Is the following, and actually I want to concentrate on the last 3 here. So if we take the diagonal element UJJ, take off the identity, and consider the real and imaginary part. So it's the imaginary part to concentrate on. So there are n of these, capital N of these, and if you take any n minus 1 of them, they're linearly independent, and they span a star subspace of K complementary to K2. So they provide the raw ingredients for a Q projection. And lastly, they have the property that the commutator of any two of them is actually in K3 is the key point, but it's in K infinity, in the smallest intersection of all the ideals. So corollary of that is the codimension of K2 in K is n minus 1, and the commutator of any two elements in K is in K infinity. So from these observations, we quickly deduce that Gaussian completeness fails when n is greater than or equal to 3. And these are easy observations that allow that. So in the remaining time, I want to say something about how we get approximate innerness and deduce from that wholly non-Gaussian completeness, and also a nice structure to further detail of decomposition of a general generating functional into wholly non-Gaussian generating functionals which live on the subspaces. So first of all, given representation of AN, then the kernel of the image under the representation of I minus UNN is an invariant subspace from rho. It's a lemma on the way to proving that the representation has a n-fold decomposition, in which the first is a Gaussian representation, and the remaining ones, they live on the nth one lives on the nth subgroup of AN, and rho n I minus UNN is injective for each of these. So consequence of that is rho n is wholly non-Gaussian, or we get no appearance at that level, n is 0. For example, if rho is Gaussian. So by living on, I mean factors through the epimorphism which witnesses the subgroup relation. Okay. So we have decomposition of the representation, and that entails a decomposition of the derivation. Now, these derivations have the property that their action on all the generators is determined by its action on the bottom right-hand element of the fundamental unitary, UNN. And further lemma is that if rho is such that it lives on the n minus 1th, one less, and rho on 1 minus un n minus 1 n minus 1 is injective, then the derivation also lives on the subgroup, n minus 1 subgroup. Okay. So next lemma, if eta is a derivation such that rho 1 minus UNN is in, and rho is a representation such that this element is injective, then eta is approximately inner, and the approximate innerness is witnessed in this simple way here. Rho of UNN is a contraction, so this is defined. And the essential ingredients of the proof of this lemma is the relations on the previous slide, giving you the value of u on general generators in terms of its value on UNN, and the simple property of Hilbert space contractions, that injectivity of I minus C implies that this strong convergence. Okay. So suppose given such a decomposition of our representation and corresponding one of the derivation as above, so we know that the first one is Gaussian, rho 1 is Gaussian, rho n and eta n now both live on an from the previous lemma, and rho n 1 minus unn is injective. And lastly, unn is approximately inner in this explicit fashion. So for each projection Q, each of these Q projections, and each n from 2 onwards, eta n, this is the bottom row of a structure map, and a structure map with the property that it leaves, that Q leaves it invariant. That's where we are now. So, in order to state the final decomposition theorem, and in particular obtain its uniqueness, we need one more concept, and that is given a subgroup B of A, subgroup, wholly non-Gaussian generating functional has full rank with respect to the subgroup if any splitting of the generating functional into a part which lives on the subgroup is a trivial splitting. That is to say, part living on the subgroup is a drift. This is trivial in this concept. So that concept allows us to state the following theorem. So given a non-drift generating functional on an, if we fix a projection gamma which leaves a projection Q which leaves gamma invariant, then gamma is uniquely expressible as, so far we've decomposed representation, rho, and the corresponding derivation. So this is saying we can uniquely decompose the generating functional such that the first one is Gaussian, and for the remaining ones satisfy gamma n composed with this projection, Q projection we've fixed. So is gamma n, so it leaves each of the gamma n's invariant and lives on the nth of the subgroups. And moreover, is of full rank with respect to so each gamma n tilde, the induced map on an, is of full rank with respect to the next one down, the subgroups, an plus 1, or it can be equal to 0. So with that, with the full rank proviso, then this decomposition is unique. So in particular, we have the sum of gamma n bigger than 2 is wholly non-Gaussian, or 0. And we have existence of a Levy-Khintchine decomposition of gamma, and it's unique, subject to the requirement that the remainder part, wholly non-Gaussian part, is invariant under the Q projection. We have a nice solution to the Levy-Khintchine problem for this family of compact quantum groups, Q deformations of Lie groups. So that is where I would like to conclude. And we've had in the last few talks, we've had reference, I believe it was 12 years and 12 weeks since your PhD advisor posed this problem. So in this case, it's this was solved for SUQ2 in 1998, so 25 years later, it was a published solution of the n bigger than 2. Okay. So there's a few other relevant references to my talk. Thank you.
We have time for a couple of quick questions. Okay,
When you pick, how much wiggle room is there in the choice of Q for the given gamma?
There is some wiggle room. It's not uniquely specified.
Yeah.
The key point in how the role it's playing here is its existence. It's basically its existence. Does that answer? I think that answers your question. Sorry.
Thank Martin again.